So last time we proved Mashka's theorem. So this brings us to the notion of a semi-simple algebra. So suppose R is a finite dimensional algebra over some field K, then we say that R is semi-simple if every finite dimensional R module is a sum of simple R modules. From this point of view, the content of Mashka's theorem is that Kg the group algebra of a finite group G is semi-simple if the characteristic of K divides the order of G. Actually, this is an if and only if. Does not divide the order of G. Correct. So for semi-simple algebras, it's quite easy to understand modules, and the main thing is to understand the simple modules. So let's just suppose I have two R modules, V which is V1 direct sum. So this means V1 direct sum, V1 direct sum, V1 taken M1 times. VR direct sum MR times, where the V1 up to VR are simples. So I know that I can do this when I have a module for a semi-simple ring. And suppose I have another one of these, W, which is V1 direct sum N1 if I don't insist that the MIs be strictly positive, then I can assume that this set of simple modules is the same, okay, because suppose some different simple modules occur in these two decompositions, I can just enlarge them to the union, and by putting some of these indices to be 0, I can just assume that the indexing sets are the same for the simple modules. So MR and NR are just greater than or equal to 0, and the VIs are pairwise non-isomorphic simple R modules. Okay, suppose I have a homomorphism T, an R homomorphism. Then I can break it up into its pieces, going from each summand here to each summand here. And because Schur's lemma tells us that either two simples are isomorphic or there are no homomorphisms between them, I can write T as K goes from 1 to R, Tk, where Tk is just from Vk direct sum Mk to Vk direct sum Nk. and this Tk itself I can write as a matrix. So if I write Vk, an element of Vk raised to direct sum Mk as, if I write this as V1 up to Vnk, Mk, and suppose I write Tk Vk as Tk Vk1 up to Tk Vk Nk. So using this column vector notation, I can think of Tk itself as a matrix. T, so here I will be putting in M1 up to Mk. So we could write it like this. As a rectangular matrix with nk rows and mk columns. So if you want to understand how this works, you expand this out as a column vector, you do matrix multiplication, and the answer is the column vector tvk. Okay? So this, each entry of this matrix Tij, this belongs to end k vk. Now if k is algebraically closed, then we know that this is k times identity of vk, right? So sorry, this is small k. So we can think of Tij as just this scalar, right? So what we have is that each Tij can be thought of as a scalar, and so this is basically just an nk by mk matrix with entries in k, right? So what do we get? We get that Hom R VW is a direct sum, k goes from 1 to R, Hom, well, okay, so this is M nk by mk k. So when you have represent modules which are sums of simples, you can always think of the homomorphisms between them as matrices. And you should check that if you compose two such homomorphisms, it will correspond to blockwise, that is for each k you will be multiplying the corresponding matrices. So if you just have one simple repeated a certain number of times, then so let me just say this. So look at the special case. Suppose V is equal to W, then what we have is Hom R VV, which I'll usually denote as end RV. This can be thought of as just k goes from 1 to R, M nk by nk. This is always an algebra because you can just compose these things, and what we are saying is that this is actually a sum of matrix algebras. So here we are assuming that the field is algebraically closed and the characteristic doesn't divide G, all that is there. So to be able to write V as a sum of simples, and for the version of Schur's lemma to hold that, you know, if V is simple, then the endomorphism algebra is just K. So that's why we need that the field be algebraically closed. So just at a combinatorial level, you can calculate the dimension of this K vector space. From this thing. So it's just the sum of the squares of the multiplicities of the simples. So we'll see later that in certain situations we'll be able to compute this using some other data, and then the equality of these things will give us a way to resolve the representation theory of symmetric groups. So this will be very important later. Okay, let's look at what other combinatorial information we can get. So let me just remind you that the center of an algebra, which is usually denoted ZR, is given by those elements of R which commute with all other elements of R. Now if you look at this matrix ring, what is the center of one matrix ring? You know that it's only scalar matrices, right? The only matrices which commute with all other matrices are scalar matrices. When I say that this is a sum of these matrix rings, I mean that addition and multiplication are component wise. So the things which are in one of the rings commutes with the things in all the other matrix rings here. And if you just think about it a bit, you'll see that the dimension of the center of this is just the number of pieces, namely R. So dimension of the center of the endomorphism algebra is just the number of different simples, no matter what their multiplicities, that occur in the decomposition of V. So here we should be careful because I said that the mi's can be greater than or equal to 0. But now if any of the mi's is 0, it will not contribute a matrix ring to this. So where V is equal to with the MRs strictly greater than 0, and these being pairwise non-isomorphic simple R modules. Okay. Oops. MIs should be greater than 0. Thank you. For all I. Okay, so now what we'll do is we'll try to classify the simple R modules for a semi-simple algebra R. The first step is to note that we don't have to look very far. We can look for all the simples inside the regular R module. So let's take R to be a finite dimensional algebra over the field K, which is, well, I guess in this case you don't need anything else. So if R is finite dimensional semi-simple, actually not even sure you need finite dimensionality. but I guess the way I've defined semi-simplicity, I assume finite dimensionality. So let's just assume finite dimensional. Yeah. Okay. So R is a finite dimensional semi-simple K algebra. Then every simple R module is a submodule of the left regular R module L comma R. Maybe I called it L tilde comma. So L tilde R comma S is just RS. So this turns R itself into an R module. And what we are saying is that if you want to find all the semi-simples, you just need to look for them inside the left regular representation. If you want to find all the simples, you just have to look for them inside the left regular representation. So the proof is quite simple. So suppose V is simple. When I say simple, I mean that it's a non-zero module. Okay, that should be understood. So since it's a non-zero module, take some non-zero element V, little v in V. Then you can define a homomorphism. So define phi V from R to V by R goes to R times. This belongs to Hom R RV. That's easy to check. And so that means that Hom R RV is non-zero. Okay, so its dimension in particular is strictly greater than 0. But we've already calculated that the dimension of this is going to just be the multiplicity of V inside R. So that means that V occurs as a sub-representation, submodule. So that proves the theorem. But we know now that we can decompose R itself into a sum of simple R modules. We've assumed that R is semi-simple, so every R module decomposes into sum of simples. In particular, the regular R module itself decomposes into. So if we let V1 up to Vk be pairwise non-isomorphic simple R modules, such that now this R itself viewed as an R module yeah, so here that phi V is phi V is non-zero at some element, and what is that element? It's the unit of. So here I should probably add unital. These will all be hypotheses which throughout this course, but it's interesting sometimes to see where they can be left out, because later on you may be interested in cases where these fail. So but usually you can safely assume that the field is algebraically closed. Its characteristic does not divide the order of the group. If you wish, you can assume that the field is the complex numbers, and all R algebras are finite dimensional, semi-simple, and so on, for the purposes of this course.
And also we can drop the condition if R not 0.
So saying that we can drop the unital condition of the R action on V is not 0. Basically what he's saying is that if you can find a vector V such that phi V is non-zero, then V occurs in the regular R module. Yeah. So if the R action of V is not 0, then it's going to be acts on V. Let's not get too, as I said, of course, on the to relax some of these hypotheses, but if you want to follow the thrust of this course, you don't have to worry. So R is going to end up being the group algebra of a finite group over, say, the complex numbers. But still, I think it's interesting to see where you need various hypotheses, because relaxing them does become important in many problems in representation. So suppose we can find certainly we can find pairwise non-isomorphic simple R modules such that we have this isomorphism of the left regular R module as by what I just discussed, this end R. So the endomorphism of the left regular R module is going to be summation k goes from 1 to R, a sum of matrix algebras mk by mk. What does this tell us about R itself? So I claim that this actually more or less resolves the structure of R for us, because suppose I define from R to end RR by using right multiplication. That means R goes to where is equal to S times. Okay, then you can check that this psi R is indeed an R intertwiner of R. But one slight irritant is that if you try to compose psi R and psi R prime, this is a little calculation everybody must do. So this is psi R prime S times R, right? I'm just expanding psi R applied to psi R prime S. That is psi R prime S times R. And that is psi S R R prime. So that is psi of, psi R prime of S is S R prime. So that's psi R prime R of S. So psi R circle psi R prime is psi R prime R. The order has got reversed. So this maps psi from R algebra to this algebra homomorphism. But it's not completely arbitrary either. It reverses the order of multiplication. So this leads to the notion of an opposite algebra. So if you have a ring or an algebra, you can always define its opposite. If you take, good question, so somebody just asked if we can take psi rs to be rs. In that case, you would certainly have that psi r circle psi r prime would be psi r prime s, but it would no longer be R algebra endomorphism unless R is in the center of capital R. Because for it to be an R, so you should check why this is an R algebra homomorphism. And that's an excellent question, because that is of course the more natural thing to do. So why am I doing this? So so you have this thing called the opposite algebra. So this as a vector space is just R. But the order of multiplication is reversed. So R times R prime in the opposite algebra is R prime times R in the original algebra. For a matrix algebra, this doesn't matter. If you just take A goes to A transpose, this is an isomorphism from matrix algebra to its opposite. Since our algebra and R is a matrix algebra, it is isomorphic to its opposite. So what we get is that this is isomorphic to the opposite of the sum of matrix algebras, and therefore it is in fact isomorphic to the sum of matrix algebras, because every matrix algebra is isomorphic to its opposite. So this is called the Wedderburn decomposition. If K is an algebraically closed field, then every semi-simple finite dimensional K algebra is isomorphic to a sum of matrix algebras. So somehow a theory which seemed to involve a lot of structure, constants and so on has collapsed into something which is purely combinatorial, in the sense that if I ask you to classify all the semi-simple K algebras of dimension 22 for an algebraically closed field K, you would just see how many ways you can write 22 as a sum of squares, and for each of those you would write down a matrix algebra. Right, so if you're just interested in algebras up to isomorphism, then it's a purely combinatorial question. Now we have these group algebras, and certainly whenever Marshall's theorem holds, they are semi-simple. So we could hope to try to realize this decomposition explicitly. So that's going to take up the rest of this lecture. What's the question? How do we prove the Wedderburn theorem? So let me just explain again. So we take the regular left regular R module. So because R is semi-simple, we know that we can write it as a sum of simple R modules. So here's a decomposition into a sum where I assume that this V1 up to VR are pairwise non-isomorphic. Then we know that what we did earlier, calculating the homomorphisms between two R modules, that this is going to, the endomorphism algebra is going to be the sum of matrix algebras. On the other hand, the endomorphism algebra is isomorphic to the opposite algebra of R. So this psi is not an isomorphism from R to end RR, but an isomorphism from the opposite algebra of R to end RR. Okay, I didn't prove that it's an isomorphism, that's not very difficult to check. So if you accept that this is an isomorphism, then you know that the opposite of R is a sum of matrix algebras. But a matrix algebra is isomorphic to its opposite via the transpose. So R itself is isomorphic to a sum of matrix algebras. Okay, let's look at the simplest matrix algebra. Suppose we have just this M and K. Let's try to understand its simple modules. So let's take this to be our R. So let V, suppose V is a subspace of K to the power n. So the n-dimensional vector space over K. This is itself an R module. In fact, you can think of this as column vectors and this algebra acting by left multiplication of a matrix on a column vector. Now, if you're given a subspace, you look at the following. MV is those matrices whose row space is contained in V. Okay, so for example, if V is the subspace spanned by the first coordinate vector, then MV will consist of matrices whose first column is allowed to be non-zero, but all other columns have to be zero. So, an easy exercise in linear algebra is that the MVs inside M and K are invariant subspaces for the regular R module. So if you take a matrix whose row space is contained in V and multiply it by some other matrix on the left, the resulting matrix will still have row space contained in V, because left multiplication corresponds to row operations. And so now if you have when is MV simple? Well, if you have a subspace, say W of V, then you can look at MW, that will be a subspace of MV, and it will be an invariant subspace. So certainly if MV is simple, then V has to be one-dimensional. The converse is also true. If V is actually one-dimensional, then MV is simple. So these will be exercises for you. They're on the homework. And dimension is the only invariant of the isomorphism class of MV. So MV is isomorphic to MV prime if and only if dimension of V is equal to dimension of V prime. So from this we have pretty much understood everything we would like to about the regular representation of the matrix algebra. So the conclusion is there's only one simple module for this algebra, and that corresponds to MV, where V is any one-dimensional space. All those will be isomorphic. So for example, if you take V to be the subspace spanned by the first coordinate vector, then you can just concentrate on the first column of your matrix and think of it as a column vector. Okay, so you will end up getting Kn thought of as column vector, and that is up to isomorphism the only simple R module. So what we get is that MNK is isomorphic to direct sum of, is actually this simple R module Kn taken how many times? N times. So this is the decomposition of the left regular representation into simples. There's only one simple, its dimension is n, and it occurs n times. Now these are the building blocks for all algebras, and what we've seen is for all semi-simple algebras of an algebraically closed field. So we just need to see how we can put together these things and get simple modules for simple algebra. So suppose you have two unital algebras R and S, and you can form the algebra R direct sum S. So its unit will be the unit of R plus unit of S. Okay, and if you have any if rho tilde M is an R direct sum S module, then from this you can construct an R module and an S module. Okay, so if this is an R direct sum S module, you look at MR, which is defined as rho tilde 1R M, and MS, which is rho tilde 1S. So take the unit. It will turn out that M is isomorphic to MR direct sum. MS has an R direct sum module where S acts on this part by 0 and R. You start with an R module MR and a module MS. R S act on this part by 0, and this gives a correspondence between modules for R direct sum S and pairs of modules, one for R and one for S. And so if you want to know what are the simples, you have to be sums. They would have to be simples for either R or for S. A simple module for R direct sum S would either be a simple module for R direct sum 0 or a simple module for S direct sum 0. Otherwise you could just take the part corresponding to R or S and get a submodule. So you can apply this to not just two but several algebras, and the same thing holds. So suppose R is just sum k goes from 1 to R M Mi M k k, then I can write any element R as R1. Maybe I should change my indexing here. Let's make it I goes from 1 to k, MIK. Otherwise I'll have R subscript R, which is not very nice. So I get R1 plus RK, where R1 is in the first matrix algebra, R2 is in the second matrix algebra, and RK is in the kth matrix algebra. So where Ri is in MIK. Now let Vi be just the k to the power mi, but I want to think of it as an R module. So I'll think of it as an R module as follows. So rho I tilde R is Ri Vi. So only the ith matrix algebra acts non-trivially on Vi. So here I have defined for you an R module. So the space is Vi, which is just k to the power mi, and the action is this R, which has a decomposition like this, will act by the ith summand. Okay, so I have defined for you an mi dimensional rho I tilde R action on Vi, thank you, is Ri Vi for all Vi in Vi. So that's the definition. So I've defined for you now. I've defined for you k R modules, and if you just think of this as a module for the ith matrix algebra, then it is simple. Therefore it's actually a simple module for R, because if it has no invariant subspaces under just a piece of the algebra, it cannot have invariant subspaces for the whole algebra. So these are simple R modules, and in fact these are all the simple R modules. So V1 up to Vk are simple R modules, and every simple R module is one of these. Let me explain that. Every simple R module is isomorphic to Vi for some I. Why is that? So if you have a simple R module, you can use this trick here to a only the ith matrix algebra acts non-trivially on the ith subspace. Okay, you take the identity, the ith identity times the module, and that gives you the ith piece. Now those are invariant subspaces, so if the module is really simple, only one of them can be non-trivial, so it is coming from only one of these pieces, and therefore it is, and since it's simple, just seen that for a matrix algebra there's only one up to isomorphism, only one simple module. So that justifies the second argument. And so what we have is now you can think of this as the k endomorphisms of k to the power mi. As an algebra, this is the standard way of going between linear transformations and matrices. So what you get is if R is a semi-simple K algebra, where K is algebraically closed, then R is isomorphic to direct sum I goes from 1 to K where V1 up to Vk are a set of pairwise non-isomorphic simple modules that such that every simple module is isomorphic to one of them, or in other words, set of representatives for the isomorphism classes of simple R modules. So that's the terminology I'll be using from now on. So we've come a little closer to realizing this thing. We saw that R must be a sum of matrix algebras. Now we've come one step closer. We know that it's the matrix algebras of the simple R modules. So now if you try to see how you can get a grip on this isomorphism. Firstly, is this a unique isomorphism? What's your question? Yeah, it seems to be non-canonical right now. Let's just look at it a little more closely. This R has a unit. So what is the unit here in terms of these things? Well, each of these has an identity element. You just add up those identity elements. Right? So that's got to be the unit of R. So we get this equation that 1 equals epsilon 1 plus epsilon R, where epsilon I is just the identity of Vi. So that's living in the ith summand here. Okay, now for some jargon. Idempotent element in an algebra just means it is equal to its square. Okay? Central means it lives in the center. That means it commutes with every element in the algebra. Okay, now you can look at primitive central idempotent. Okay, before I come to this, let me just give you some examples of idempotents. Each of these identity elements is an idempotent, right? But also inside these, if I think of these as matrices, I can write down idempotent matrices. For example, this is an idempotent matrix. Okay, but this is not central in the algebra of 2 by 2 matrices. So if you ask what are the central idempotents, you'd have to take identities from some of these components and add them up. So this itself is a central idempotent. But there's something special about these. These are the building blocks of the central idempotent. So these are called the primitive central idempotents. And if you want an abstract characterization of them, then it is the following. So it's an element epsilon which satisfies two things. Well, of course, one is that epsilon is a central idempotent. And the second is that you can't break it up further into central idempotents. So if epsilon equals epsilon prime plus epsilon double prime, where both epsilon prime and epsilon double prime are central idempotents. Then either epsilon prime is 0 or epsilon double prime is 0. So you can't break it up into more central idempotents. So now we know completely what this algebra looks like. It's a sum of matrix algebras. So if you just think about it, you'll see that these are the only primitive central idempotents. Okay, so you'll have to work through this. It's not completely obvious, but it's not difficult either. And so that means that these guys are abstractly characterized by these intrinsic properties of the ring. Okay, but once you've got hold of these, you've got hold of these things, because this is just the two-sided ideal in R generated by epsilon I. If you just the identity in the ith component and multiply it on the left and right, well, all the other components are 0, so what you'll end up with is the full endomorphism algebra for the ith component and zeros everywhere else. So you'll end up with this ith summand. So in that sense, this decomposition is unique. These matrix algebras are uniquely determined by R because of this intrinsic characterization of the generators for these two-sided ideals. So these are very special elements in our algebra. And let's try to compute these for a group algebra. So that's certainly interesting.
My understanding, right, the force of these last few theorems is that those epsilons are the only coupling between the group itself and the K algebra. That everything else, aside from those epsilons, everything else in R is completely boring with respect to the group.
So your question is, how important are these epsilon i's somehow? If we understand the epsilon i's, do we understand R completely? Exactly. The answer is in many senses yes. We'll have to think about a precise formulation of that question, but you'll see that if you can calculate the epsilon i's, you can reconstruct, for example, you can reconstruct decomposition as I just pointed out. So in some sense you can, you've understood completely the structure of the, you've explicitly got the Wedderburn decomposition for the ring R. But if you ask if knowing the epsilon i's allows you to give a construction for each simple R module, I'm not so sure what the answer to that question is.
R epsilon I R is you're multiplying epsilon I with R.
Yeah, so R epsilon I R is just all possible products of one element of R times epsilon I times some other element of R. For example, if you take a matrix algebra and you take the identity and you multiply on the left and right, well, you just need to multiply on the maybe one of these is redundant. As I pointed out, epsilon I is central, so R epsilon I is epsilon IR. Okay, but then I'd have to decide whether to write R epsilon I or epsilon R IR. So you can just write R epsilon IR. But I see what your question is. Okay, so no need to be intimidated by this. It could be either this or this, and you're right. These are central, so it doesn't matter. Okay. Okay, so to solve that, we need a few tricks, and this you'll really have to go home and think about quite a bit. I'm going to do it quite fast. So firstly, there's the notion of tensor product. So if I have two vector spaces, V and W, finite dimensional, let's say V has basis V1 up to Vn and W has basis W1 up to Wm, then traditionally we just think of the tensor product as the vector space with formal basis given by symbols Vi tensor Wj, where I goes from 1 to n and j goes from 1 to m. And this is how mathematicians and physicists have worked for a long time. There's a coordinate free definition. For example, you'll find this in the book Survey of Modern Algebra by Birkhoff and MacLean. So you should go look it up. And what it says is that a tensor product is not just a vector space. So this is a vector space, but it's not just this vector space, but it comes with a bilinear map from V cross W to that vector space. So let me just say that there exists a bilinear map from V cross W to V tensor W. And in this case, it's just V comma W maps to, say Vi comma Wj maps to Vi tensor Wj. A bilinear map is determined if you say what happens on a basis of this and a basis of this. So let's call this D. No, B for bilinear. Such that for every vector space U and a bilinear map D from V cross W to U, so whenever you have a bilinear map from V cross W to any vector space, there exists a D tilde from V tensor W to U such that D is D tilde circular. So this is the modern category theoretic definition. Here let me just show you how you can use this definition. So for example, suppose I have S an endomorphism of V and T an endomorphism of W, two vector spaces, then I can look at D of V comma W to be B of SV comma TW. So this goes from this is a bilinear map from V cross W to V tensor W, right? Because B goes to V tensor W and it's bilinear in these things. So this being a composition is also bilinear. So this is from V cross W to V tensor W. So according to this definition, there should be a linear map from V tensor W to V tensor W. So usually you draw a picture like this. So here we've got B and this is D and there's a linear map D tilde. Okay, and in concrete terms this ends up being, well, from our point of view we can define it, but this ends up being what is called the Kronecker tensor of S and T. Another notion that we need besides tensor product, the linear functionals on V. And you all know that if you have an endomorphism of V, you can define an endomorphism of V prime. And this has the property that if I take T prime and apply it to some linear functional, well, I need to get another linear functional on V. So I can feed it a V, and it turns out to be C of TV. That's the definition of C prime. So this is this corresponds to the transpose if you choose a basis, and so it has the property that if S circle T prime is T prime circle S prime. Now you can define the contra gradient of a representation. So this is something like this is again the basis free way of saying that the transpose is an isomorphism of a matrix algebra with its opposite. You define the contra gradient of a representation. If you have a representation rho comma v, you can define a representation rho prime on the vector space V prime by saying that rho prime of G is, I would like to say rho G prime, but that won't be a representation because of this order. But you compensate for that by putting an inverse here. So this becomes a representation of G on V prime, and this is called the contra gradient representation. Okay. Now those are the pieces we need. Now let's play the game. So I'm going to consider three representations of G cross G. So let's fix firstly rho comma some representation of G and consider the following three representations. Firstly, I can think of KG as a representation of G cross G. I've already mentioned this before. There's the left regular representation and the right regular representation. One comes by left multiplication, the other comes by right multiplication. These two actions commute. So you can really just think of it as a representation of G cross G. Explicitly you write it as, so remember KG, you can just think of it as functions on G. So what happens if I take G in G, H in G and apply it to the function f? So I should get a new function. Let me evaluate that function at a point x, and the answer is f of G inverse xh. You can just check that this is a representation of G cross G. Here's another familiar character. We've so far thought of it as an algebra, but now I want you to think of it as a representation of G cross G. How do you do it? You have an endomorphism of V, so you can compose it with any other endomorphism of V on the left or on the right. So you use these two things. So I call it E rho. This depends, of course, on the choice of rho comma V. So I have T, which is an endomorphism of linear endomorphism of T and of V, and I want to say how this acts. So I'll just compose it. Probably have to put an inverse here, or no, maybe not. Well, let me just put that there. I have to check if it's right or not. And the third is using the Kronecker and the contra gradient. So V is a representation of G and V prime is a representation of G. Now let me explain to you how these things are related. So we know that, so let's just see some intertwiners. Again, I'll leave the checking to you. So from V prime tensor V to Kg, you can write down an intertwiner as follows. So these kinds of things will span V prime tensor V. And this should go to a function of G. So that function takes G belonging to G to Z rho G V. So given a linear functional and a vector, you can construct a function on G by this formula. This is called a matrix coefficient of rho G for the following reason. Suppose you take a basis of V, then you get a dual basis for V prime. And if you take the ith basis element here and the jth dual basis element there, then this turns out to be the ijth entry of the matrix for rho G. And this turns out to be a G cross G intertwiner. And the other one is between these two, and that's in fact an isomorphism. You may have seen it if you've studied abstract tensor products before. So the second one is V prime tensor V to NGV, which is given by Z tensor V goes to. So now I need to take a vector in V and tell you where it goes. So it goes to Zx V. So physicists often denote this by this symbol. So it's a rank, this is going to be a rank 1 endomorphism because its range is just spanned by V. When you take mixed tensors, you can get higher rank endomorphisms. And this turns out to be not just a G cross G intertwiner, but an isomorphism of representations of G cross G. So now you apply this to a family set of representatives, isomorphisms of symbols. So suppose V1 up to Vk are a set of representatives for the simple representations of G. So then you could now I want to claim that this is actually an isomorphism. The reason is the following. Well, there are several steps again to check here. I'm assuming that Vi is simple. Using that, you can show that Vi prime is a simple representation of G. Okay. Now suppose you have two groups, G and H, and you have a representation V of G that is simple and a representation W of H that is simple. You take V tensor W and think of it as a representation of G cross H. That will also be simple. This is something that needs to be checked. Okay, many proofs of this fact go using character theory, but we will be using this to derive character theory. So the burden of proof now shifts to this very important fact. So each of these is a simple G cross G module, and this just on each piece is a non-zero G cross G intertwiner. Therefore, it must be injective. Okay, so it's injective on each piece. And the other thing is we already know that the dimensions match up. So this is an isomorphism. Again, several steps need to be checked very carefully. Now here we've got this thing, just this isomorphism from up here. Good point. So you want to know why the fact that it's injective on each summand implies that it is injective on the direct sum. So let's ask, what could the kernel be? Okay, so the kernel would be a sum of simples. So it would be a sum of a subset of these summands. But that means that but none of these summands could be contained entirely in the kernel because it is injective on each summand. So that's the reason. Again, I'm going through these things much faster than one would do in a normal course. So you would have to work through these, and I've tried to arrange the homework problems in such a way that you actually get a chance to think through all this carefully. Okay, so combining these things, we should get some isomorphism here like this. And that will be, this is quite explicit, and so this will also become explicit, hopefully. So here we have to figure out, if we take the identity here, what will happen to it. So here's another thing that connects these two pieces. So you have V prime tensor V to K. This is just a bilinear. So V prime cross V to K, you have a bilinear map which takes Z comma V to Z is a linear functional, V is a vector. You can evaluate them, right? So by the abstract definition of tensors, you get a linear map from V prime tensor V to K. This we know is isomorphic to end KV. Maybe I should put a. So can you guess what this will be? So you want a linear map from linear endomorphisms to the field. And somehow this is interesting. It turns out to be the trace. Again, you have to work this out. This is one of the most important points, and this is why trace of a representation plays such an important role in representation theory. This is where it first appears. So in terms of this picture, what it is that under star, this isomorphism here, suppose I have T in end KVI, then T goes to trace of rho IG circle T. In particular, the rho IG. Okay. So as G cross G representations, the identity here goes to the trace of the representation itself. But there's some room for moving things around here. As G cross G representation, this is simple and it maps onto a simple part. I could scale the thing and still get a homomorphism. Okay, now the Wedderburn decomposition is such an isomorphism, and I have constructed such an isomorphism, using this picture. So the two must differ on the simples by some scalar. So I haven't shown that under the Wedderburn decomposition epsilon I goes to trace of rho IG, but what I've shown is that epsilon I goes to something which is a scalar multiple of trace of rho IG. So all we have to do now is resolve those scalars. So what we've concluded is that under the Wedderburn decomposition, epsilon IG is some constant times trace of rho IG, where this is of K. Now let's just look at the following thing. As the decomposition of, well, maybe I should write it like this. You look at the decomposition of the KG, the regular R module, then we already know that the ith simple occurs as many times as its dimension, right? Now, if two representations are isomorphic, you can check that their trace is apply trace here and I can apply trace here. So what do I get? I get, if you take LG and look at its trace on KG, so that's right. So what is going on here? G will just take a function and translate it by G. So if you take the basis 1 subscript x here, it will go to 1 subscript gx. So this entire basis gets moved if G is not the identity, and the entire basis gets fixed if G is the identity. So you'll either get trace of 0 or you'll get trace of trace equal to cardinality of G. So this is cardinality of G times delta x times identity of G. It's, and on the other hand, this thing is so this is same as 1 times the unit of kg, right? Cardinality of G times the unit of kg. And so what you get is that the unit of kg, now if I expand the right hand side, I just get 1 over cardinality of G summation I goes from 1 to R dim Vi trace of rho Ig on Vi. That this is summation I goes from 1 to R epsilon I. Okay, and I know that these terms are linearly independent and that each of these summands is a scalar multiple of these. So each of these summands must be equal to these. So what we get is epsilon I is dimension of Vi divided by G times the trace of rho Ig on Vi. This explains the central role played by characters in representation theory. Okay, I'll stop here.